Bismillahirrahmanirrahim. Hi guys, how are you doing? We will start chapter 5, Newton's laws of motion. Let's start with the contents. Newton's laws of motion. This is the first title. Second title, applying Newton's laws. Third title, friction. Let's start with Newton's laws of motion. Two of the most important quantities in physics are force and acceleration. You studied before the meaning of the force and also the meaning of acceleration. As you have learned, acceleration is the rate at which the velocity changes with time. So, the symbol for acceleration A equal the change in velocity over time, or V final minus V initial over delta T, or T final minus T initial. The unit of acceleration, as you see, the unit of a change in velocity meter per second over the unit of time is second, so the unit of acceleration meter per second square. This is the unit of acceleration. The acceleration may be positive or negative. When the object speeds up at a specific time, so it is positive acceleration. When the object slows down, it is negative acceleration. Let's speak a little bit about force. Force is quite simply a push or a pull. A push or a pull. Like when you have like a box and you start to pull this box, you are exerting or applying a force. Or you have another box and you are pulling it. So push, this is pull or push. So you are exerting a force. Two quantities characterize a force. The strength means the magnitude, the numerical value, 10 Newton, 20 Newton, 30 Newton of the force. Second quantity that characterizes the force is the direction in which the force acts. So, as you learned before, that force is vector quantity. As you know, we have two types of quantities, scalar quantity and vector quantity. The one that needs a direction, we call it vector. So, like the force, like the velocity. But if you have a quantity that to define it well, you need only magnitude, we call it scalar. Like time, like volume, like area. So, acceleration is a vector quantity, it has magnitude and direction. Also, force is a vector quantity, it has magnitude, or what we call it is strength and direction. Let's go to next slide, Newton's laws of motion. Objects do not start or stop moving on their own. This observation is the essence of Newton's first law of motion. So, when the summation of force equals 0, we are dealing with Newton's first law. You can say Newton's first law with different type, with different sentence. Like this one, an object at rest means its velocity equals 0 remains at rest as long as no net force acts on it. So the summation of forces acts on it equals 0. So the object that at rest will continue at rest. And an object moving with constant velocity We said that velocity has magnitude and also direction. So when you say constant velocity, the magnitude doesn't increase or decrease, and also direction is a straight line. That means constant velocity. The magnitude, the numerical value is constant, and also the direction will be a straight line. So an object moving with constant velocity means constant speed and in specific direction, straight line, continues to move with the same speed and in the same direction as long as no net force acts on it. So, in Newton's first law, we have two cases. The first one, an object at rest will continue at rest as long as no net force acts on it. The second case, an object is moving with constant velocity, will continue moving with this constant velocity as long as no net force acts on it. So, Newton's first law discusses the summation or the net force acting on an object equals zero. The object at rest will continue at rest, and an object moving with constant velocity will continue moving with constant velocity. Put in your mind, when you have like a table and you start to move something on it, after a while it stops. It stops because there is a force of friction acts in opposite direction. So we can't apply here Newton's first law because there is force of friction, and we said that the net of forces equal zero. That happen in space. When something moves far from any planet, it continue moving at constant velocity as long as no net force acts on it. What we spoke about in this slide is the Newton's first law, or you will know later that we call it law of inertia. Law of inertia, and you will know the reason of that. Newton's first law of motion contains the phrase no net force. No net force, so the summation of forces act on an object is zero. What does this means? The net force is the vector sum of all the individual forces acting on an object. Imagine that I have an object or a box. There is a force to the right 10 Newton, and the force toward the left 5 Newton, and another force toward the left 5 Newton. So when you try to get the vector summation for all forces acts on the box, the summation equals zero. So the net force acts on the object is zero. Another example, when you sit on a chair, there are essentially two forces acting on you. Imagine that you have a chair and you are sitting here on the chair. There is force of weight downward, right? Your weight. And there is another force normal to the chair, perpendicular to the chair, that we call it Fn, or the normal force or the support force. And both forces are equal in magnitude and opposite in direction, so you are staying at rest. The upward push of the chair, that what we call it normal force, it is perpendicular, it is from the chair on you, and the downward pull of gravity, that what we call it weight. Since you are at rest, the two forces must cancel out. They are equal in magnitude, opposite in direction. Therefore, the vector sum of the forces or the net force acting on you is equal to 0. Here we discussed an object at rest will continue at rest as long as the net force equals 0. Newton's laws of motion, we still with the first law. Our experience tells us that an object such as a box being pushed across the floor will stop. Right? If you push something on a floor, after a while will stop moving if you stop pushing on it. This occurs because of the force of friction. The force of friction always be in opposite direction of the direction of the motion. The force of friction always be in opposite direction of the motion. So this occurs because of the force of friction acting between the box and the floor. What would happen if the force of friction could be eliminated? What will happen if you eliminate this force of friction, make it smaller so the object move further, right? Until it stops. Let's complete here. While friction cannot be eliminated completely, but there is a way to eliminate it, but not completely. It can be greatly reduced. Like the figure here. The figure below shows a device known as an air track. It's a track. It has a small holes as you see. Yani it's shaped like that. And there is holes here. And we push air. So the cart here, above it, like it is flying. So with this way, you eliminate the friction between the cart and the track. An air track provides a cushion of air on which a cart can ride with virtually no friction. So you can move the air track here or the cart with less friction but you have to push air here inside. When placed at rest on a level track, the cart will remain at rest until given a push. In accordance with Newton's first law, once the cart is in motion, it will remain in motion until acted by a net force. In theory, if the track could be made infinitely long and perfectly frictionless, as we can, the cart would continue moving with a constant velocity forever. And that's what happened in space, guys. Newton's first law is sometimes referred to as the law, as we said, of inertia. What we mean by inertia? Tendency of an object to resist any change in a state of motion. The object likes to stay in its state of motion. If it is at rest, like to stay at rest. If it is in motion, like to continue movement. Loosely speaking, inertia means laziness. Kasal. Objects may be thought of as lazy because they do not change their motion unless forced to do so. So, if you want to move an object, you need a force or if you want to change the movement of an object, you need a force. If you want to speed up of an object, you need a force. If you want to slow an object, you need a force. If you want to change the direction of an object, you need a force. So the meaning of inertia is the tendency of an object to resist any change in its motion. That's what we call it inertia. Do you remember, guys, this experiment when you get a cup and a card above the card and you put like a coin and you try to move this card quickly? What happened for the coin? What happened for the coin? It will not move with the card. It will stay on the bottom of the cup. Why? Because the coin at rest and likes to stay at this motion. That's what we call it, like to stay in this state of motion or in rest. And the opposite example, like when you are riding next to your father in the car and suddenly he stops, he pushed the brakes. Your body will try to move forward. Continue moving because your body was at movement. So, the meaning of inertia again, tendency of an object to resist any change in motion. That's what we call it inertia. So, Newton's first law speaks about the net force equal 0. An object at rest likes to stay at the same state, and a moving object with constant velocity likes to continue moving with constant velocity. So there is a big relation between Newton's first law and the meaning of inertia, tendency of an object to resist any change in its motion, like to stay in its motion, if it is rest or in motion. Newton's second law. Let's go directly to Newton's second law, or what we call it law of inertia. Sorry, law of acceleration. The first law we call it law of inertia. Second law we call it law of acceleration. Newton's second law of motion tells how a force changes an object's motion. Throwing a baseball requires less force than pushing a car and giving it its same speed as the baseball. Why? What is your opinion? Baseball has less mass than the car. The car has a lot more matter, more mass than does a baseball, right? It is hard to push a truck than pushing a bike. Right, guys? Here is difficult to push the truck because it has more mass. So, we're still working on Newton's second law. That's what we call it law of acceleration. An object's mass is a measure of the amount of matter it contains. The meaning of mass, guys, what is mass? The amount of matter in an object. And it is measured in kilograms. The unit of mass is the kilogram. Here is the table below. Provide a list of typical masses. Not for memorizing, guys. Not for memorizing. Gives you the mass of Earth, space shuttle, blue whale, whale shark, and so on. Okay, guys? Baseball. The mass is measured in kilograms. This is the SI unit for measuring mass. Newton's laws of motion. How does an object's acceleration depend on the force? The experiment here illustrated in the following figure show that the acceleration is doubled when the force acting on a cart on an air track is doubled. Imagine that you double, here is the force. Here is double the force. So if the mass is the same, what happened for the acceleration? Acceleration increase. The acceleration double. So F directly proportional with acceleration, or we can write it in better way, A is directly proportional with force. When mass is constant, acceleration is directly proportional with the force. And also, what happened when the mass is doubled? The acceleration becomes half. So A inversely proportional with the M. When you double the mass, the acceleration becomes less, half. As you see here, how does an object acceleration depends on the mass? The experiment illustrated below show that the acceleration is halved when the force acting on the cart is doubled. The acceleration is halved when the force acting on the cart is doubled. Let's wait. Not when the force acting on the cart is doubled. There is a mistake here. Here is the force is the same as the force. What is double? The mass. So we can rewrite this sentence. The experiment illustrated below showed that the acceleration is halved when the mass is doubled. When the mass is doubled, the acceleration becomes half. Well, don't forget the meaning of acceleration, the rate of a change in velocity, delta V over delta T. So, the results of the two experiments can be summarized by saying that an object's acceleration directly proportional to the force, as we wrote before, and inversely proportional to the mass. So A inversely proportional with M. So from both, A directly proportional with F, inversely proportional with M. This is mathematical statement of Newton's second law of motion. Guys, some students like to make the equation like in a triangle. F equal ma. So if you need to get the mass of an object, F divided by A. If you want to get acceleration of the object, F divided by M. If you want to get F, so F equal ma. A equal F over M, and M equal A F over A. Rearranging the equation as we did yields a form of Newton's second law that is perhaps best known. F equal mass times acceleration. You need to know that. It is found in any physics book, guys. Force equal mass times acceleration. F equal ma. Force is equal mass times acceleration. Let's speak about the units. SI unit for mass, kilogram. SI unit for acceleration, as we said before, meter per second square. So the unit of force, kilogram meter per second square. We call it kilogram meter per second square. We call it Newton. The abbreviation is capital letter N. So I can say that the force equal 5 kilogram meter per second square, or 5 newtons. The unit of force used is the Newton. And Newton is defined as the force required to give a mass of 1 kilogram and acceleration of 1 meter per second square. I want to know how to define a Newton. F equal m times a. If the mass is 1 kilogram and the acceleration 1 meter per second square, so the force is 1 Newton. So the Newton is a force applied on a mass of 1 kilogram. It will accelerate 1 meter per second square. So the Newton is the force required to give a mass of 1 kilogram, acceleration 1 meter per second square. Put in your mind that Newton is roughly equivalent to a quarter of a pound. Okay? Pound is British unit of measuring force. The table below gives the magnitudes of some common forces. Main engine of a space shuttle, as you see, the number of newtons, 31 million Newton. What you are important, the forces that accelerate a car, 7,000 Newton. The weight of an apple, 1 Newton. The weight of a rose, 0.1 Newton. So let's go directly to some experiments or some examples. The following example illustrates how Newton's second law is applied to calculate the force. You know well, put in your mind, F equal ma. Let's read. And 1800 kilogram car, so you have the mass, and it is in kilogram. It is important to take care of the units. Has an acceleration, so you have the acceleration, and it is in meter per second square. What is the force acting on the car? So F equal ma. 1800 times 3.8 equals 6,800 Newton. So easy, guys. Let's go directly to next slide. The second law also applied to situation in which several forces are acting on an object. So you need to get the vector sum. When several forces act on an object, the F in the equation, F equal ma, is replaced with the sum of the force vector. And you need to get the vector sum. The notation sigma F is read sum of the force. Let's stop here, guys, and it is not enough for the first lecture, and directly go to the second part to watch some problems to solve it. God save all of you.